So today we can talk about vectors. So vectors in space, they have a direction and magnitude. For example, my arm has a magnitude, which is the length, and direction, which is where I'm pointing it. But a scalar has magnitude only. So a vector, we can draw this in a 3D plane like that. If we multiply this by a scalar, then let's say 2, then it doubles the length. So it doesn't change. If we multiply vector by a scalar, it doesn't change the direction, it just changes the length. So let's call this vector A, and we put a little arrow on top to remind ourselves that it's a vector. So this vector has components in the x, the y, and the z directions. So these are just unit lengths. So if I have a vector that goes 1 in the y direction, my j is going to be 1. Then let's say 3 in the z direction, my k is going to be 3. And 2 in the x direction, my I is going to be 2. So we can decompose x, y, and z, or the vector, into its components. So a1, a2, a3. This just equals a1 in the x direction plus a2 in the y direction plus a3 in the z direction. So if we want to have the magnitude of vector A, then we can just put this. It's the same notation as absolute values, basically. So let's say if we want to find the length of a vector with components 1, 2, and 3. I suggest that you try this yourself, but I will work through it in a couple of seconds. Okay, so I'm thinking that you've all tried this, but I will work through it now. So if we want to find, then we can just have the square root of the squares of all the components. So a1 squared plus a2 squared plus a3 squared. And this will give us the length or the magnitude. So this is actually going to be a scalar quantity since it's a numerical value. So let's just plug these values in. That's going to equal the square root of 1 plus 4 plus 9. This equals just the square root of 14. So we can visualize this vector, and hopefully it will give you a better intuition of the magnitude. So this is going to be y, x, and z, and the components are going to be 1, 2, 3. It's going to be 1, 2. So this vector is going to be stemming from the origin, and we can draw it. It's quite hard to draw, but it's like that. So this is going to be A. And we can see the vector here. So this is just going to be in the xy plane. Y, x, and this is just going to be 1, and this is going to be 2. So the height here, this is of course going to be 3, but we can just ignore that, and we can call this vector B. So B is going to be a vector with components of just 1, 2, and 0. So we can visualize this on the xy plane, where this is going to be B. This is just 1 and this is 2. And of course we can find the magnitude of this. This is going to form a right triangle. So the magnitude of vector B is going to equal the square root of 1 squared plus 2 squared. Since that's the components, we can ignore the z since it's 0. So this is just going to be square root 5. And as you can see, this height is going to be 3. So we can draw that, or we can visualize that vector A is just going to be 3 here. So if we kind of turn the axis, we can see that this is going to be vector B, and this is going to be the z component of A, which is 3. And we can find the magnitude of this, so this is going to be vector A. And the magnitude here is just square root 5, and this is 3. So we can sum up all the components, so that means the magnitude of A is going to equal square root 5 squared plus 3 squared. This equals square root 5 plus 9, and this equals square root 14. So this is probably a better visualization of why we just square all components and put them into a square root. So in general, if we want to find the magnitude of a vector, we can square root its components and just and this works for thousands of it works for every dimension. It works for 1 dimension, 2 dimensions, 3 dimensions, infinite dimensions, and you just have to keep summing up the components. Now let's talk about vector addition. So if I have A and I want to plus another vector B, let's first visualize how this will look like. Z, and let's say I have a vector here, okay? This is going to be vector A. And then let's say I have vector B right here. So what we can do is we can either move this to point it like this, so we could get something like this, and this will be the resultant vector C. we could also do this where we put b, but it will also be the same result. As if you see, we can put b over there and it gives us the same result. But how do we actually compute this? So, as we said before, A has components A1, A2, and A3 in the X, Y, and Z directions respectively. And we can also, same thing for B. So what we do is we can just add the components of A and B. So this will be A1 plus B1, A2 plus B2, A3 plus B3. So a better visualization of this is, so let's say I have B and I have A like this. What we can do is we can move B so it starts at the end of A. So this will just be B, and the resultant vector is going to be A plus B. And you can see that no matter which table, we can put this over here and we'll get the same resultant. So we put vector A on the tip of here and we get A. And this result is the same. So how we can compute this is as we sum up the components of the vectors and then we get the respective the resultant vector in the X, Y, and Z direction. So now we can talk about the dot product. So the dot product is a way of multiplying two vectors and getting a scalar value, a number. But how do we actually compute this dot product? So if A has components A1, A2, A3, and B has components B1, B2, B3, then the product is just going to be the sum of AI, BI, or in the respective components. So this is going to be the X component of A multiplied by the X component of B plus the Y component of A times the Y component of B, and so on and so on. So if you don't know what this is just the sum of. So this equals A1 B1 plus A2 B2 plus A3 B3. So now let's work through a problem. Let's say A equals 3, 7, 6, and B equals 1, 2, 3. What will the dot product between these two vectors be? So hopefully you've tried to work this out on your own. So I will work through it out now. So the dot product of A and B is just the respective components multiplied and then summed up. So this can be 3 times 1, so 3 plus 14 plus 18, and this is going to equal 35. And that is going to be our dot product. What does the dot product mean geometrically? So another way of writing the dot product is the length of A multiplied by the length of B multiplied by the cosine of the angle between them. But what does this geometrically mean? And how is this the same as summing up the components? So number one, let's say if we have a vector and we have a dot product between that itself. So this tells us that this is going to be the length squared times the cosine of theta. But since this, if we draw it, this is going to be A, and this is also going to be A. So cosine or theta is going to be 0, cosine is going to be 1. So this tells us that the dot product between this is just going to be the length squared. But recall our previous definition. So if we have with components A1, A2, A3, this is going to be A1 squared plus A2 squared plus A3 squared, which is indeed the length squared. So this is just going to be a quick review of law of cosines. So we can use law of cosines to calculate this, of course, but so this, we can say that this vector C equals this vector A subtracted minus this vector B. So we can say that this is A plus minus B, or negative B. And since this is just a scalar multiple, we can multiply each component of B by -1. Such, now we have negative B1, negative B2, negative B3. So if we want to find the magnitude of this side, so C squared, we'll just use that. You can square root it, but this is the law of cosines. So we have A squared plus. So this right here is Pythagoras, but since this isn't always a right triangle, we have a few extra terms. 2. And so these are just the magnitudes, of course. And this is the law of cosines. So now we will see how our original dot product, A1, B1 plus A2, B2 plus B3, A3, B3 equals theta. So now this is going to be, we can see that this looks like that, and now I will start proving it. So what I did first, as you can see here, I've written down, so this is just the previous law of cosines, and as we see from here, C equals the vector A minus vector B, and we can square this. So this, as we proved earlier, this is going to be this, since this just equals A dot A. And we can see that C equals the vector A minus the vector B, and then dot product with C again. And we can expand this using the FOIL technique, and this works for dot products. So we have A dot A, you can see that that's the same from here. A dot B minus B dot A, and these are the same thing. So this is how we get this term, and this of course is again a dot product with itself, which is just the length squared. And that's how we get this. And this looks a lot awfully similar to the law of cosines, right? So we have the magnitude of A squared plus the magnitude of B squared minus this 2 times this term right here. And if you believe in the law of cosines, then this can just be a proof that dot B is indeed equal to the magnitude cosine theta. And hopefully I know how many of you could be able to derive this. So this is a proof that A dot B equals, in fact, the length or magnitude of A multiplied by the magnitude of B times the cosine of theta. So one application of the dot product is finding length and angles. So how can we do this? So let's say I have a point A that is at 1, 0, 0. Then I have B that's at point 0, 1, 0. And I have a point C at 0, 0, 1. Okay, so we can see that these points form a triangle in space. And let's say we want to find this angle right here. So first we can have, first we can figure out the dot product of the quantity of B dotted, so that's going to be this, and dotted with a C, and this of course just equals the length of the vector AB times the length of vector AC multiplied by the cosine of theta. But hold on, we have another easier way of finding the dot product, and that is A1 B1 plus A2 B2 plus A3 B3, right? But I don't want you to just be confused by this is just B, and so I don't want you to be confused with this B and this B, okay? This is just our formula, and it doesn't have anything to do with these vectors right here. So first, we can find this vector, A and B. So A and B, the vector is for a vector, it doesn't matter if you're centered at the origin or wherever. So this is going to have, we can just write this that has -1 in the x direction. So we can write AB -1 with 1 in the y direction. And 0 in the z direction, but we don't really need to put that here. And so AC, this is going to have AC equals, of course, this is going to be -1 again. And the height is just going to be 1, so this is going to be 0 since it doesn't move in the y direction. It's going to be 1. So remember, we can use this formula to calculate, and this multiplied by this, so this is going to equal, we can just write this equals this multiplied by this, which is going to be 1, plus this times this, which is 0, and this times this, which is 0. So the dot product is just going to equal 1. So, what can we do with this? We know that this product is equal to 1, and we want to find the angle of here. And we can easily find the magnitudes of this vector and this vector. So, let's first look at this vector right here. So, this is a 90-degree angle. This is going to be 1, and this is going to be 1, 2. So using Pythagoras, we can figure out that this is just going to equal square root 2. Similarly, this is going to be 1, and this is going to be 1 also. So this is going to equal square root 2. So all in all, 2 cosine theta equals 1. And we can solve this. So this, of course, is going to be pi divided by 3. And what we can figure out again is, so this is going to be pi divided by 3. But, so if we want to specify, if we want theta, right, if we want theta, then we can divide both sides. So we have AB the vector dot AC the vector divided by the magnitudes of AB multiplied by the magnitudes of AC equals the cosine of theta. And if we were to compute this again, then we'd end up with 1/2. We'd end up with 1/2 here, and this being cosine theta. We have our cosine here, and we have theta equals pi divided by 3. When they form a 90-degree angle, and it's going to be less than 0 if they form an obtuse angle like this. So really, the dot product is just a measure of how the vectors follow each other. The closer they follow each other, the higher the dot product.